Howdy, everybody. Hope you're doing well, wherever, whenever you are. We're here for day 7 of Advent Code 2017, trying to plug along, solve more problems. One's called Recursive Circus. Recursion, that could be fun. Let's find out. Wandering further through the circuits of the computer. Oh, that's a good question. We're in a computer. There's a circus. You come upon a tower of programs that have gotten themselves into a bit of trouble. A recursive algorithm has gotten out of hand. Now they're balanced precariously in a large tower. Oh, maybe it's like one of those circus acts where they're like, one program at the bottom supports the entire tower. It's holding a large disk, and on the disk are balanced several more sub towers. The bottom of these sub towers, standing bottom, are other programs holding their own disks and so on. The very tops of these sub towers may program this balance, but with no disks of their own. Okay, so if I have that right, it's like we're building a tree. Directed acyclic graph. You offer to help, but first you need to understand the structure of these towers. You ask each program to yell out their name, their weight, if they're holding a disk, the names of the programs immediately above them balancing on name, weight, and programs immediately. Okay. You write this information down. Excuse me. Unfortunately, in their panic, they don't do this in an orderly fashion. By the time you're done, you're not sure which program gave which information. For example, if your list is the following, then you'd be able to recreate the structure of the towers that look. This is the tree. We know. So the key to this is we presumably there's only one, right? It always says there's one, but each other one could have multiple. There's a trick. We know this one is actually the top because, or the bottom, I guess, because it's not found over here, right? So it has nothing that it's a child to that makes it the top or the bottom. At the bottom of the tower is holding up these. Those are holding up other programs. So none of the programs are holding up any other programs, and are all the tops of their own tower. Actually, before you're ready to help them, you make sure your information is correct. What's the name of the bottom program? Okay, so the idea is, I think we can create them. Well, we just need to know what the bottom program is. So I actually think we just need these values and these values. We just want to track which ones we've seen and not seen. And there will be only one. Oh, you might be able to do set different between this list. And that'll solve part one. I suspect we'll have to parse this. So maybe we still try and parse it. And then for P1, we just do the set list of them. What is the name? How many are there? Is that right? 13, 37. Okay. Yeah, there is a lot. And it's not always three, right? There's multiple of them. Okay. Interesting, interesting. So again, I think, oops. Did I do that? like this. And then we do line map print new. We'll have some new function. Parse. Don't think I have to do it there. So we split by space. Thing. So we'll say let people. Oh, I actually want to return program. That. So we'll say the name is parts. Size equal parts dot next. Or no, it's weight, right? Rim. How does this work? Matches. That, does that work? So, okay, that's a very ugly line, but I think that works. I could probably just elide the. Okay. I can actually, let's call it so. So now we skip the next. And then, right? We skip this one. And then the rest of them are the comma-rated list of children. So we do like let children equal parts dot. Huh? Return name 8. That. Well, it compiles at least. We actually want to do 2 hash sets. So we'll say like keys or like names children. equals this dot hold set alt uh, mm, mm. And so we'll do name dot insert names dot insert name, and then program dot insert. What am I returning? The bottom one. So it's actually, so I'm actually returning a string. Uh, oh, I'm names differ. Cool. Okay. Names dot difference. Children. Does it need to be a reference? Dot select. Dot like that. And let's see. Uh, that. But for P2, I'm just going to do weight is unused. No. We're still blowing up. Oh, it may not have any. So I just do what first on text. If it's true, or E. I guess we don't care what this. There is one. We return that. Another one. Return back. That. Okay, it passes, and it gave me this answer. What do you think the odds this is right? It is right. Okay. Again, so like, oops. I mean, we did some parsing, right? Um, which we didn't necessarily have to do. But for part one, we're just trying to find the root node. And like the easiest way to do that is to literally just do a set difference of the two, right? Um, that is, like, just to be clear, on this side you have all like the programs, and on this side you have their children. Well, the one that's at the root is not a child of any of them, right? This one at the root right here is not a child. There's nothing before it. So you just need to have a set of the children and a set of these, and then that will. So that does part one. Too shabby. Part two. The programs explain the situation they can't get down. Rather, they could get down if they weren't expending all of their energy trying to keep the tower balanced. Apparently, one program has the wrong weight. Okay, that's we hadn't used it yet. It was for part two. Until it's fixed, they're stuck here. For any program holding a disk, each program standing on that disk forms a subtower. Each of those subtowers are supposed to be the same weight, or the disk itself isn't. The weight of a tower is the sum of weights of the program in that tower. The example above, this means that for UGML, disk, talent, those three must all have the same. So these three have to have the same weight. However, for TK and K to be balanced, the program standing on its and all programs above it must be matched. So this plus this 68, 50, this 243, this. As you can see, this one's unbalanced. Yeah, this one's heavier, even though the nodes above them are balanced. So this one is balanced. This one, so this is the one that causes heavy. Given that exactly one program is wrong, what would its weight need to balance the entire time? Okay, interesting. I mean, I think we just do like a DFS style thing, right? Like we'll just start at the root node and we'll say, are all of its children balanced? One of them won't be. Find the one that's not balanced. And then we'll say, are all of its children's balanced? And if there's ever a case where it's balanced, the children are balanced, but it's not, then it's the one. But you also kind of need to know, like, you need to know like, this is saying it's off by 8. So you kind of need to keep track of, like, um, the odd weight, like the bad weight, the odd 1 ounce weight, right? Man, this is crazy. Well, I mean, I know how we can start. Um, that, and this actually isn't going to return a string. This is going to return a beat. Turn row for now. Okay, we'll quickly start using those. Um, we're going to do some DFS at the root node. We want to have the expected weight. Wait, what is the turn? Iterator over. Oh, we want to collect this. So we actually need to. So map root 0. Like, this is what I'm expecting. This is what, like, my neighboring weights are. It's going to be something like this. Oh, I need to keep track of weights too. I don't want to do a bunch of recalculation. So, like, we'll do that. So we'll have like FN DFS. It's not a DFS, is it? Reverse, yeah. Is any I want to have this return an option because it may be that one is not imbalanced. I don't know. Let's just start programming it, and we'll start working through it. So we want to get our child programs and their recursive weights, right? So it all. Something like that. So get all the children weights, find the odd one out. If there is none, I think it's like that. So we'll return 0 for now to get rid of this. So we'll say let program uh, ooh, I actually just want to calculate their weights first, right? Like I want to have like a this is the cache function is like get the total weights. Should I do that in like a separate thing, like just go through and get the total weights once? Like could I add a field here that's like So this is like a recursive function. And this is where I actually think we want to cache. Like if we've seen the weight before. We get immutable reference to her. This is not going to work. Cannot add law. Is it not going to let me do this? I just have to do let program. Borrow, there's first borrow, there's huh? Closure requires unique access to the map, but it's already borrowed. Can I not include my map? Like that's what it suggested. I can't include. Why is that? I need to do like this. I think this is the same. Say, not move out of. Do I just clone it? Oh, so cache dot insert. I actually don't know if this cache is going to help. I've this. I definitely don't want to. Not happy about. Okay, I've gotten rid of all the errors. I think that works. That this is going to give us all of our total weight. Yeah. And then we want to. We now know our own weight and all of our children's weight. So we just get all the children weights. We say let equals round hitter. Yep. Yep. C. Dot. That. Spell it right. So this is all our children weights. How do I determine if any of them are unequal? Like there's got to be like a find an odd one out. Is it like for each of the weights, we do like the problem I'm having is like, and I don't know why this is such a struggle. I ought to think this, maybe I just haven't done this in a while. But like, you want to find the one that's different, but there may not be any that are different. And so you might think, oh well, I'll just pick the first one and see how many are different from the first one. But how do you know if the first one's not the odd one, right? Maybe all of them are different. Oh, is that what we do? Is we say, maybe we write a function this one. We do fn find odd one. Um, children, spec, size, and we're going to return if it's an odd one. Return index. Yes. We say if 0. I think that's it. Like, I guess we can just say if children dot is less than else. Oh, and then we say similar equals children dot filter. Or we could say if all So if they're all the same as the first, then there is none. Otherwise, we know there is one that's different. How do we know which one is different? Am I overcomplicating it? What if I just do something like or or I see if like what I want to do is like just go through all of them and see if there's any where it's where all of the children are dissimilar. So if I don't find any, I'm going to return none. So I'm going to do like if children iter filter e see dot. I want to return I like that. This doesn't work though if I have to do another check, right? I have to and we're equal to 2. That so we could say if let some odd find odd one. Oh, but how do I know if I'm the odd one? I'll have to think about this. Find the odd one out. No, I just do if let some odd. I'm the odd one out. I know so I've found an odd one, right? It's like something like that, right? I feel like I'm getting close. I don't need the cache anymore because I've done all the recalculation. Whatever the odd one is, that's what we want to do next, right? So we traverse map odd. Total weight. Oh, it's just children. Oh, this returns the index. So it's actually going to be program. Like that. I mean, it's actually returning. Oh no. Well, the test is failing. The left is 251, right? 6. I mean, it's actually finding. I'm inclined to like once I've found it. That BM. So it actually does find the right one. It's just not giving me the right number. And it's because the child, I know it's a UGML. I have a 68. I'm returning 251. Oh, I want my own weight. So I'm actually going to return this weight is should be a weight of a child that's not me. So like let other equal, not equal. 43. Okay. So it's going to be program dot what is my weight? plus these can't be U sizes. I may have to do some subtraction. Let's find out. Okay, so this, okay, I think that wasn't too hard. So it's going to be plus, it's going to be my current weight plus the weight minus total. That work? Think it's that? Please be. Got it. Okay. That was actually a lot tougher than I thought it would. It it's a tree traversal problem at its core, right? I wonder if I have some issues in so but I think like the possible problem is we actually want like I'm gonna try something. Uh 8 that to give you the same answer. It actually does. So I actually think it is this way. What I was thinking that was going through my mind was is it how do you calculate the weight difference? But I think the notion is that I have the weight of my neighbors and I have my own weight. And the difference of the weight of my neighbors and my own weight is going to tell me how much I need to add or subtract from myself. And then that will tell me what my weight should be. I think that's right because if you imagine these two numbers, what they're saying is like, here's how much I'm off. And it may be that you need to add weight to get to that, or you need to remove weight to get. I do think that. Okay, that part one was super easy. What did I do it in like? Well, I did do some parsing, but it took like 10 minutes, 15 minutes, like 13 minutes or something like that. And if you include my parsing, but it was really just find the difference of these two things. Part two is much harder. I had to think about that for a while. But what do you do is so I first traverse the graph and get all the weights, the total weights of all the things. And I do that with a cache so I don't have to like keep recalculating. But basically what I'm doing is in the map, I'm setting what my total expected weight is. So I do one quick pass and then that allows me to do the traversal and say, you could probably do these in one, combine the two, but it felt easier to do it this way. And it finishes pretty fast in microseconds, right? But then in my main traversal, right, I want to get all the weights of my children. I know the root is not going to be it. So this weight is invalid at that point, but I'm going to get all the children. I'm going to find the odd one. And if there is no odd one, then I know that I'm the odd one, right? Um, I actually don't know if this will happen. You might be able to remove this because presumably it's not a leaf node. Yeah. Like, I don't like, what is that saying? If you think about the way the tree looks, like if you ever got to this one, that one would be the odd one out. And so you'd say none, there are none because there's no children, so you'd never get down to here. So I think this is correct. This price. My initial thinking was, oh, do I need to check to make sure there's more than two? But I don't think you do. Like if it has no children, there's no odd child node. I think that's maybe the way to say it is. Right. So if it has no children and we're actually here, then there is no child node that's the odd one. It means I'm the odd node. And so I have to track this weight, and this weight is like the weight of the nodes that come before. So we are in this one, we are doing like I think it's a BFS, right? We're gonna try. I mean, we're just gonna do a search. Call a search. Because we have a tree, we're going to find the odd one out, right? So we're going to go through the list and we're going to say, here's all the children, which of them are odd? And it actually, I think because we pre-calculated, it happens pretty fast, right? Because we'll immediately get to this one and we'll say, well, are all of its, which one of its children are the odd ones out? It's this one. We go here, then we say, which one of our children here are the odd ones out? And it's none of them, so then we know it's this one. So because we did the first pass through, I think it happens faster. You could potentially, again, I think, do the set total weights and then the search in their own thing. But this is like a tree search thing. You can see I've solved tree problems for like, I don't know, 20 years. And it still takes some thinking, right? Unless you've worked with like a specific tree structure for a long time. It takes a little bit of thinking. So be patient with yourself and be patient with me. Maybe you're screaming at the screen. I think the reason why it takes a long time is because it's a recursive in nature. And I had to keep thinking about some of the weird edge cases. Like, what are the leaf nodes and how do I get, you know, for example, this weight, it should be like, I mean, this should actually be called other weight. Like, that's what I'm actually interested in. Like, what's the other weight minus my weight? I'll give you. Okay. That was much harder than the previous day. I think the previous few days have been comparatively easy, right? We had like a really tough day 3. Anyway, it was fun. I had a lot of fun doing this. It's fun to work through these problems and solve them. I don't know about you, but like my day has gotten like much more AI oriented. AI has really picked up. And so like I'll often have like 2 or 3 agents doing things and I'll be like moving 2 or 3 agents, different stuff. That's like my new job. It's just like checking AI's work. Um, but it seems to make me more productive, at least at work. And so I miss it. And so it's nice to be able to like try and solve a problem. So There you go. I had a lot of fun. Hope you had a lot of fun too. Sorry, I always stare here because my OBS is over here, like on this side. And so it's like, I realize I should be staring at the camera, looking at you, right? Anyway, I'll get better at that. Thanks everybody though. I had a lot of fun. Hopefully you had fun too. Um, point out all my flaws and my errors in the comments, and we'll talk to you next time. Thanks everybody. Bye.